Okay, this part we will be looking at the group 1 metals especially. Okay, but these group 1 metals will also, or these trends will also apply to your group 2 metals. Okay, group 1 metals are called alkali metals. Okay, why are they called alkali metals? It's because if I have sodium with water, if it reacts with water, this will give me my NaOH plus H2. Okay, it's about balancing up your equation. So when I react my group 1 metals, it will give me the alkali, the hydroxides. Okay, first part, we are to recall your metallic bonding. This is electrostatic force of attraction between the cations and C of delocalized valence electrons. Okay, so I have like cations here, cations, cations, right? And then the electrons are delocalized. So the electrons could be here, it's all moving around the whole structure, and that's my metallic bonding. So there are some physical properties that we have to know for your group 1 metals. They are low density, they float on water. Okay, other metals, your transition metals especially, usually they will sink to the bottom. Okay, they are shiny and silver when cut, or shiny silver when I cut it, all right, and then they are dull. When I leave, after I cut it, I leave it to open, it is dull and gray. So dull and gray is typical metal color. Okay, why is it dull? It's because it reacts with oxygen in the air. They are very reactive metals. They form a layer of metal oxide, and the metal oxide is a dull gray color. Okay, metals are soft, malleable, and ductile. So pure metals contain metal cations, same size, and then they are regularly orderly arranged. Okay, and then I have a sea of delocalized electrons. So when I apply a force on this side, right, these cations can actually slide over, and the electrons, because they are delocalized, they are moving, it allows these cations to slide. Okay, so allowing these cations to slide over one another easily without breaking the metallic bonds. All right, so they are known to be soft, malleable, can be bent into thin shapes without breaking, and ductile. I can pull it into wires. They are good conductors of electricity and heat. Okay, to conduct heat and electricity, I need to have what we call mobile charge carriers. Okay, mobile charge carriers to conduct both heat and electricity. Okay, so what is acting as the mobile charge carriers is the sea of delocalized valence electrons. The electrons that are moving around within the structure allows the transfer of heat and electricity. Okay, group 1 metals generally have low melting point, low boiling point. This is comparatively low if I compare it with all the other metals, example your transition metals. Okay, what is the explanation for low melting point, low boiling point? Down the group, atomic size increase due to increased shell. This one we already established previously. So there is weaker electrostatic force of attraction between the cation and delocalized electrons, because I'm talking about metallic bond. If I want to melt or boil metal, I'm breaking the metallic bond. Okay, smaller amount of energy is needed to overcome the weaker ESFOA, so they have lower melting point and boiling point down the group. Very common explanation they will ask us to write. Okay, so these are all your physical properties. Let's look at the chemical properties. Okay, for chemical properties, essentially this is how reactive your group 1 metals are and what is the trend. Okay, so reactivity will increase down the group. Same explanation, atomic size increase because there's increased number of shell, period 1, period 2, period 3. There's weaker electrostatic force of attraction between the cation and sea of delocalized electrons. Okay, your ESFOA is between what and what? We have to write it exactly as it is. So it is easier to lose this valence electron because I have weaker ESFOA. And then when my metals lose electrons, it forms the cations. It can react with other elements. Like for example, it reacts with a non-metal to form your ionic bond. So the reactivity increases down the group. Exactly the same explanation as your melting point, boiling point. Okay, the alkali metals tarnish easily. Alkali metals tarnish easily. Okay, the alkali metals tarnish easily by reacting with oxygen in the air, so they are stored under oil to prevent this reaction. Okay, and then when the alkali burns in oxygen, they have characteristics flame color. So lithium is red, sodium is yellow, so this is my sodium, potassium is lilac. Okay, the first three colors, especially my sodium and potassium, we have to know. Okay, and then because reactivity increases down the group, these metals will react quickly with water, rapidly, show a trend, right, for your sodium, and then violently for your potassium. So we can see that reactivity increases down the group, right? It gets faster and faster. Okay, so generally, the important thing over here is write these words that I just underlined to show the trend, as well as be able to write the equation. So most importantly, my water in a chemical reaction is H plus OH minus. Okay, so my lithium, which forms Li plus, will kick out the H plus. Lithium will partner the OH minus to give me my alkali, right? That's why they are the alkali metals. And then my H plus doesn't partner anybody, will partner itself to form H2.